Hey, let's get started. Good afternoon, everyone. Welcome to lecture 22 of computer architecture. Today we're gonna start this new topic, interconnects. It's not a new topic, but it's a new topic in this course, like for this semester, let's say. We have seen actually the importance of interconnects in many different lectures, and you know that we discussed about this long discussion between is the problem, is the bottleneck is the memory or also the interconnect? And as you know that we believe that actually both memory and interconnects are actually the bottlenecks in our system. Since actually memory also involves a lot of interconnects, how you connect banks in your memory module also, all these involve these kind of questions. So this is a just very brief overview of our last few lectures. So we discussed about multiprocessing fundamentals. Yesterday, we also seen memory ordering, which is consistency as another word, and cache coherence. And this is a recall for yesterday's lecture about two cache coherence methods. We discussed a Snoopy bus that essentially caches are connected to a shared bus, and they are snooping the bus, like observing the bus, and they are updating some metadata which are related to coherence protocol, depending on things that are happening on the bus. So the effectiveness of a Snoopy bus is really dependent on if we can have a bus, essentially. Having a bus for a small multiprocessor is possible, like 4 cores, 8 cores, I don't know, 16. But at some point, the effectiveness of bus is not that good, because when you add more nodes to the bus, you need to reduce the frequency of that bus. And then your communication latency will become actually higher and higher. And at some point, you get to basically scalability issues. But there are also some ways that you can actually make a virtual bus in a network. So you can have a network and then create a virtual bus, but that also needs a lot of that needs a lot of effort in order to make it work, and that can actually cause a lot of races. And how you basically handle these broadcast packets in your network is not really easy. So that's why actually people also look into directory-based techniques, that essentially you have a directory which is actually adds a step to the critical path. Now, when you want to access your memory, you need to first consult with the directory and then get response. And then based on that, you can do whatever is needed. So you can, of course, distribute your directory across different nodes, and each is good. So directory can be scaled in your network, but it also has some issues as well. But both of these, Snoopy bus and directory, can also motivate why we need interconnects and why this topic is actually quite important. So we will start about concept of interconnects, not only in the basically like interconnects in general, which also called as interconnection network, that you don't consider on having an interconnect only on the chip. It can be actually interconnect on a board, or can be also in a supercomputers, that you have several switches, and these switches actually overall, they are making an interconnect. We have seen also Venice work in the SSD lecture, that for example, we devised a mesh network there, but that mesh network was not actually on the chip. That mesh network was on the SSD board, which is system on board design, essentially. So today we are mostly discussing about interconnects in general, and we're going to learn a lot about that. But next week, we're going to focus more on chip networks. What are the basically potential, or let's say limitations, that we have when we want to design interconnects on the chip? And these are already things that I mentioned about the Snoopy cache and directory. And that brings us to interconnection network lecture. Before I start this lecture, I also like to announce quickly, because I got a lot of questions about exam. So the exam is happening on December 19th, as you already aware. I think this Thursday, right? Thursday before the Christmas. So we will have the exam actually in the lecture time. So from 1 p.m. to 4 p.m. And in our actual lecture room, which is ML F39, we also reserve ML F38, just in case if we don't have enough space in that. But essentially, it's just a normal lecture time. You just come and do the exam. And we're going to also schedule some problem solving session or discussion session, let's say, that we're going to solve some exam questions and answer to your questions before that. So we will announce it also, hopefully, soon. So I think I answered the questions, mostly important questions about the exam, but feel free also to ask if you have. Yeah. So, yeah, so I think our TAs are, some of them are working on them, some of them are delaying. So the final, basically all grades, like the labs, homeworks, and reviews will be out in early February, essentially, because some of the deadline for them actually is end of January, right? So we will spend some time in early February to grade those stuff. But for homework questions, we will do our best, but at the same time, we also release solutions, right? So you can check also the solution and see, basically learn about the answer. But we will also try to basically release your grades on homework questions as soon as possible. But I cannot promise. Yeah, fall semester is always quite hard due to many deadlines that you will see also later when you start PhD or master. Okay, so any other questions? Good. So these are some very important readings for this lecture. The first one, these two actually are very important papers. We will discuss this paper, actually a case for bufferless routing, I think next week. Professor Mutlu will discuss it. And this one is also about a paper about like packet, exploiting packet latencies like in on-chip networks. These are important readings that you can check. We also suggest some other readings as recommended. We're going to see them in your homework 5, essentially. Okay, let's start with some basics. So the first question is that where is interconnect used? So essentially the answer is simple. Basically, we use interconnect to connect and communicate between components. And these components can be actually anything. Like we have many examples, like when you want to communicate processors with processors, when you want to communicate processors and memories, like memories bank or cache banks, or for example, caches and caches. Like in a non-uniform cache access, NUCA, you put a lot of cache banks in a network and you make a basically bigger cache with that. Or when you want to connect IO devices. Or for example, if you want to connect CPUs, GPUs, and cache banks and some other accelerators. So essentially, whenever you want to connect some components, that component does something, essentially you need interconnect. And interconnect enable communication, as you can see. And these are like two examples of that interconnect can be, for example, connect, so in both shared memory system and also message passing system. So in shared memory system, you have a storage modules, or let's say memory modules, that they are shared across your processors. And then these processors are using this switching network or whatever, interconnects essentially, to communicate or to access your storage modules, essentially. But interconnect can be also considered as you have different nodes, and each node is actually a complete processor, like a processor and a storage, like complete, let's say, computer. And then these computers can be connected through the network, right? And with this structure you are using in your parallel programming, you need to use this paradigm of message passing. If you know about MPI, for example, message passing interface, this is actually make more sense for such a structure. For shared memory paradigm, we are usually using such stuff, that you have a shared memory. With CXL, actually, you can have even bigger shared memory that you already, I guess, you know about it. So yeah, so with that, you can use this shared memory paradigm in order to program. But yeah, so interconnects is essentially useful for both systems. We need that. So why is it important? Just to conclude again, like it affects the scalability and cost of the system. Essentially, how you can effectively connect all these nodes, right? So this is important. That affects the scalability of your system and also cost. Also affects performance and energy efficiency. What's the latency to access in the network? If your network can sustain enough throughput or not. For example, you might have a network that you can access with low latency, but that network can only work when there are not many requests at the same time. So that means that if you have a lot of requests, then your network will be saturated very soon, and then latencies will be quite high. So essentially, the design of network interconnects would affect the performance of the system a lot. Energy efficiency, you can also assume, right? So how many hops, or let's say how many steps you need to take in order to reach to your destination node, and in every step, how much power you're consuming. So all these would affect energy efficiency of the system, and it also affect reliability and security. For example, there are some networks that from one node to another destination node, there is only one pass, let's say. So if something happened to that pass and you got some faulty nodes or faulty links, let's say, then basically this node is unreachable to that. These two nodes are not connected anymore. And that's actually caused reliability issues, essentially. So people actually have worked also a lot in this line to provide path diversity and also make sure that routing algorithm also benefit from that path diversity in order to avoid these reliability issues. But at the same time, interconnect can also cause security issues. Like interconnect is a shared fabric across different cores. And whenever you are accessing a cache, for example, your message to that cache bank can be actually observed by other cores as well, because you have a shared medium here. And people have worked a lot, actually, to use that interconnect as a side channel such that they can get information. They can leak information. So interconnect also involves a lot of parameters and goals. When you want to design it, here in this table, you can actually see there are many parameters, like the number of processor, like the number of processor ports, like how many ports for memory you are considering, what should be the peak bandwidth, average bandwidth, message latency. Is your interconnect has quality of service or not? Should we satisfy some service or not? What we do about reliability. So for example, this interconnect claims that no message loss. So that was the goal for this interconnect, to make sure that it's reliable. And what's the availability? So there are essentially a lot of parameters of processor memory interconnection networks and goals that you need to consider them and basically design your interconnection network. And I should say that actually interconnection network is a very dense topic that involves a lot of stuff, a lot of detailed stuff. So if you want to learn about it in detail, I would recommend this book, Principles and Practices of Interconnection Network, from Bill Daly and Powell's. So this book actually is the one I also actually read this book, and it's a beautiful book. So I would recommend, if you have time and if you're interested, check this book. And interconnection network, actually in some universities, they allocate one big course for only interconnection networks. So it's actually that's true for every topic that we discuss in this course. So this course, we wanted to share a lot of exciting topics to you. But if you really want to go deep into any of these topics that we discuss, you really need to allocate a big course to that. Interconnection network is also one of them. So another example of why interconnect is also important is actually, you can think of clock distribution network. So we have a problem about distributing clock. You know that, I guess all we know about clock signal, that we use clock signal in order to synchronize across our modules. So the problem we have is that clock signal arrives non-uniformly or non-uniformly late to different parts of. So we know that clock will arrive to the points late, because from the source of clock and destination, there is a distance. But the problem is that we have non-uniformly late. some component receive clock earlier and some of them later. So, and that can cause potential timing issues. And you know that we call it clock skew in digital design and computer architecture. You may know it from those courses. So the solution is that we'd like to design the interconnect to equalize the arrival time of the clock signals to all parts of a chip. So that's the solution. And people actually have developed different clock network. This is actually one of the famous clock network, which we call it H3. And the goal for H3 was to make sure that people can basically clock arrives at all locations at roughly the same time. So if you know about clock skew topic, you know that this clock skew effectively increases both setup time and hold time. I hope you know what is setup time and hold time. Okay, good. So I don't need to explain, right? Anyone wants me to explain? Don't be shy. Good, great. So yeah, clock skew effectively increases both T setup and T hold. So that's basically is very important to make sure that every component, all the components in the system, they observe the same clock. Basically, they observe the same peak and low in clock signals. So you can check these papers if you want to learn more, but essentially people have developed a lot of different networks for clock. And this is also the interesting diagram for this processor alpha clock skew spatial distribution that you can see in the chip from the vertical axis and also horizontal axis. You can see what's the skew for the clock. So even that people actually put a lot of effort in distribution of the clock, still we have that problem. So essentially, I mean, this interconnect is a big problem, honestly, for everything that you want to communicate. It's not only for clock, but this is just an example. If you want to learn more, you can check this lecture, Timing and Verification, from our DDC course. But now I want to basically jump into interconnection networks, basics, and I will start with some boring stuff, some terminologies. So interconnection networks, unfortunately, involves a lot of terminologies that I'm gonna actually mention them in a few slides, but hopefully we will get to more exciting stuff as well. Any question? I'm not sure actually. Yeah, but it's good to check. yeah. Okay, so the first terminology is actually topology, which is topology specifies the way switches are wired. So essentially the graph of switches, the way that you connect switches or routers, let's say, that defines your topology. So topology essentially affects routing algorithm, how you route your messages from a source to the destination. It affects reliability. As I said, there are some topologies that they provide only one connection from one node to another node. So those topologies are fundamentally, they are not providing good reliability, because if that link or that connection just get broken, then you cannot reach to that destination node anymore, which is not good. Also, topology involves, can define your throughput, how much throughput your topology can sustain, depending on how many links or how many passes you can provide. Also, topology can affect your latency. There are some topologies that sending a packet from one node to another node, you need to basically take a lot of hops. So essentially, your topology has a long diameter. We're going to get to that terminology also later, which is, so you need to, basically your distance can be very long, depending on the position. But there are some other topologies that they try to reduce that long distances, and they can provide better latency, essentially. And another point, which is very important, that affect actually all other stuff, is how easily you can build that topology. There are many, actually, if you check, if you just do some research on topologies that people have proposed in interconnection network, you can actually see a lot of exciting ideas, like a lot of like many exciting graph structure that they can provide. And they actually show a lot of good reasons for such topologies. But in the end, this item, building ease, is a very important metric here that can actually, that can cause that mostly in our network on chip design, when we want to have interconnect on the chip, you don't really go that fancy in the interconnect. So you mostly use like topology similar to mesh, for example, or rings or hierarchical rings or hierarchical bus or things like that, essentially. But there are many also other topologies that they can be actually used for supercomputer as well. So in supercomputers, because your topology or your interconnect is actually happening through switches, which are, they are not on the chip. So you can think of connecting many things, you know, you have more, hopefully, possibility. But on the chip, you always need to care about this building ease, which is very important. A routing algorithm is how does a message get from source to the destination. So in your topology, you know that there are some passes that from those passes I can get from source to the destination. A routing algorithm essentially tells you that, okay, among all these passes, how you can get to that. And there are many versions of actually routing. There are some routing that they only offer you one solution, like this. Every time you ask the routing algorithm, says that, okay, from this source to that destination, this is your routing. There are no other routings. There are no other passes. But there are also some routing that they are more adaptive. We're going to actually see that. And they can offer many other versions of routing. As I said, it can be static or adaptive. People also say deterministic and adaptive. So there are many of also different terminologies here. Another important terminology here is buffering and flow control. So what do we store within the routers and links? So essentially, flow control says that when you want to go from a source to the destination, when you want to send this message, so you know the path. So you know the path because you know the routing. But the way that you go from this source to the destination, how you move your packet, how you move your message in chunks or not, or whatever. So these actually is the message of flow control. So if you want to, for example, go from one node to another node, do you make connection or acknowledgement or, you know, to the destination, to the next router, that in the terminology we call it downstream router. So upstream and downstream. So you send a packet or a message from upstream router to the downstream router. So this needs some communication. So there should be some buffer, for example, in the downstream router, such that that downstream router can buffer your data if there is a blocking. But that being said, there are also some network design that you can have them bufferless. Is actually one of the very exciting work that we're going to cover next week, that your network does not have buffer, essentially. And that's actually involves a lot of exciting topics in flow control and routing that we're going to see later. So this actually involves that, okay, your flow control is based on the entire packets, or is parts of packets, or etc. So you're going to see more when we get to that part of lecture. And how do we throttle during oversubscription? Sometimes you're overloaded and you want to reduce the load, you want to throttle. So how do you basically essentially throttle? So all these are topics of buffering and flow control. And this is actually tightly coupled with routing strategy, as you know, as you can imagine. Any questions? Okay, good. Another important terminology is network interface, which is a module that connects endpoints, which can be processors or caches, to network. So essentially, when network usually is considered as a network of routers, and then each router should be connected to a cache, or essentially should be connected to the processing element or a node. And that can be cache, processor, GPU, accelerator, whatever. So in order to connect a router to the processor, there is a module named network interface. That network interface connects that router to that processor, essentially. These actually these structure make more sense when you want to really decouple your network and the processors and caches. But there are also some network design that actually network is tightly coupled with your processor and cache design. So that's things you don't really need maybe network interface. or network interface can be actually integrated in your processor chip or router chip. So it does not need to be a different chip or different structure, essentially. You also have link, which is bundles of wires that carry a signal. So essentially, two routers, when you connect them, or a processor to router, you call all these bundles of wires a link. And links can be several wires. They can be like 8 wires, 128 wires, for example, 256. So there are many versions of that, depending on your cost and essentially the way that you design your router or your network. Another important topic is switch and router. So these two are sometimes interchangeably used, even though overall in the terminology of an interconnection network, routers are more complex than switches. So switches usually are quite simple. You can consider them they are only switch, and somehow you need to reconfigure that switch, the way that basically it connects the input to the output. But router essentially involves a lot of decision making. You can think of router might be more intelligent than switch. So there are parts of router that does this arbitration and making decisions and try to allocate resources to the requesters such that it can optimize the bandwidth, essentially. But switches are overall less complex. But that being said, there are also some papers that they just use them interchangeably. And and you can see that this is to connect fixed number of input channels to fixed number of output channels, essentially. And channel is a single logical connection between routers and switches. So you can think of channel is actually very similar to link, but the only difference here is that channel is a logical, basically, terminology. Like when you discuss about topology, which is a graph, you talk about channels. Like you say that this topology provides like 8 channels, for example. But the fact that each channel, like how many links actually can build that channel, or what's the bandwidth of that channel, or these stuff are more related to link. So when people want to provide more detailed information, they usually use terminology of link. So, question? Are these terminologies surprising, or they make sense somehow? Yeah. Yet more terminology. We have node, which is the router or switch within a network. We have a message, which is unit of transfer for network's clients. So when processor or a cache wants to send a message, some data basically, to a destination node, we call it message. And you might actually want to send a lot of messages. So basically one message is unit of transfer for network's client. And packet is actually a unit of transfer for network. So essentially what you want to communicate to the destination, that might involve a lot of messages. But then when you want to send every single message in the network, you need to send it packet by packet, because your network is actually designed to handle packets. And that's exactly also the case in our, I guess, networks. How many of you have taken network course? So these terminologies, I guess, are kind of similar, right? They're also, yeah. And fleet is actually a flow control digit. So once we get to the flow control, you're going to see that when we want to send a packet from one node to another node, we usually send it fleet by fleet, essentially. Okay. And these are hopefully last terminologies. We, depending on the way that you design your network, you can categorize them in direct or indirect networks. So in direct networks, endpoints sit inside, or we call it direct, or outside the network. In outside, we call it indirect network. So this is an example of indirect network, that these are your endpoints, like processors. You have 16 processor or caches, for example. And here also you have 16 again. So these can be actually the same or different nodes. So you can also think of 16 processor here that they are connecting 16 cache banks, let's say. And this is your network. And you can see that endpoints are outside of the network essentially. So that's why we call this indirect network. And each of these are routers or switch. And the radix of, so we call them radix of 2 because they have 2 inputs and 2 outputs. Sometimes people also call it radix array, or so these routers are 2 array essentially. So this is indirect, and this is an example of mesh network, which is direct network. You can see that end points are actually inside the network. Question? Good. Okay, now let's dive into topology. And I start with more terminologies. So in the area of topology, we have regular or irregular topologies. So regular topologies are those topologies that essentially your topology is a regular graph. That from every point that when you look at your topology, you see the same thing essentially. So ring is actually one of them. Mesh is considered as one of the regular network, even though mesh is not completely regular because of these nodes. You know, these nodes have only 2 connections, or this node has 3 connections essentially. But people usually also consider mesh as a regular network. And irregular, something beyond that is irregular essentially. At some point, I will also use Blackboard to show you some more stuff, but I don't think you need examples for regular or irregular, right? Makes sense. Routing distance is a number of links or hops along a route. So whenever you want to send a packet from a source to the destination, there are some certain number of hops or links that you need to take. So that's actually called as routing distance. However, diameter is actually maximum routing distance within the network. So diameter is actually is defined by the topology. So if your topology are, let's see here. So in this network, for indirect network, your diameter is 4, right? So for example, assuming you want to go from this node to this node, you need to go from all these steps, like this one hop, another hop, another hop, and another hop. So you need to take 4 hops to reach to the destination. But how about diameter in the mesh network? So of course, diameter is actually from this node to this node. And you need to go essentially, I mean, this is one way. You go X, and then you go Y, and you get to the destination. So you can see that actually the diameter of the mesh network is actually quite high. An average distance is the average number of hops across all valid roads. So this can be actually defined uniformly. Like you assume that your traffic pattern is completely uniform and random. Like every source can send a message to every destination with a equal chance. So if you consider that kind of traffic pattern, then you can actually calculate average distance, right? But people also use this average distance for any traffic pattern. So sometimes your traffic pattern, you might use a network which does not really have a good diameter, like the diameter is long, but the traffic pattern is usually that you use is more or less a neighbor. So most of the time you only communicate to your neighbors. So you rarely go to that far distance nodes. So in the end, your average distance for that kind of traffic would be much low. And that can actually cause some, I mean, depending on your usage, but that can also mislead people. For example, say that, okay, this network, the average distance that I calculated is, for example, 3. Like in mesh network, if most of the time you just communicate with your neighbor, your average distance would be around 1 or 2 or 3, something like that, right? However, if your traffic pattern is uniform, your average distance would be something around, in this example, I guess 8 or so, right? So yeah, but yeah, people, sorry, yeah, I will get to that. People get calculate average distance sometimes it's numerically, with mathematics. So with mathematics, they assume that basically they have completely random traffic. But sometimes people calculate or measure average distance. Actually, here is measure because they measure average distance using simulations. And with simulation, they assume some traffic patterns, and that traffic pattern can actually affect your average distance. Yes. Yeah, I mean, this is yeah, that's true. Of course, you can also consider this inject. So you need to inject your packet to the network, and then you need to eject, and that's always +2. So that's why we don't. I mean, it also depends on the. So you always need to have the exact definition that you know what you want to report, but usually people don't report that injection and ejection. That's true, actually. Here is 3 hops, for example. Yeah. Okay. Another very important, actually, terminology is bisection bandwidth. And people use this bisection bandwidth in order to compare many topologies together. So bisection bandwidth essentially is often used to describe network performance. So when you cut network in half, and then some bandwidth of links basic that they are served, like the minimum number of channels is spanning 2 halves times bandwidth of each channel. Like in a mesh network, if you want to calculate the bisection bandwidth, you need to find the way to cut the network to half, and then see that how this half to another half is connected, right? Do we have a lot of channels or not? And you can actually see that you can actually make a lot of nice analogy in road traffic as well, right? There are some cities that from one part of the city to another one, there are not many channels. Like, for example, in Istanbul, I guess I know that there's only one channel. Yeah. And that's always, there are a lot of traffic jam in that channel, right? So that's exact. But that being said, that really depends if your traffic is actually going far distance. If you're mostly communicating neighbor, sometimes you don't want to spend a lot of energy or a lot of cost to make a lot of very good bisection bandwidths, right? So it very depends on how you want to design your network, depending on your workloads. You really need to optimize, because if you just want to, if you design a network that should work well for every, which I don't think is actually possible, that we design a network which work well for every possible scenario. But if you have that kind of mindset, you're gonna get to a network which is quite costly in the end, right? So you always need to optimize your network with your goals and with your essentially workloads that you are thinking. Yeah, I remember that Istanbul traffic because I've been in that traffic, so that's why. But that's is not only Istanbul has that issue. I think many cities actually have the same. Yeah, yeah. In the city that I studied my bachelor, master, and PhD in Tehran, actually, we also have that issue. Whenever you want to travel from west of city to the east, it's just a headache. And I remember every morning I had to travel from southwest to northeast. Nika is laughing because she knows what I'm saying. Yeah, from southwest of city to northeast, and that could easily take 2 hours. So 2 hours to go to reach to your destination, and kind of 2 hours when you want to go back. So yeah. Yeah, I guess all cities, they have such issues. I mean, probably they were thinking that people should work more or less locally, such that you have neighbor commute, but that's not happening because the resources are not that balanced, I would say. Okay. Another very important terminology which actually can affect your performance is your network blocking or non-blocking. So if connecting any permutation of sources and destinations is possible, network is non-blocking. Otherwise, network is blocking. So you have many, like every pair of source and destination, there is a connection, right? If you want to make all these connections at the same time, and still your network can sustain, then your network is non-blocking, which is very hard to achieve, essentially. And most of the time, our networks has some blocking aspects. So depending on your chance, depending on your current traffic status, you might not be able to reach to your destination. That doesn't mean that your network is unreachable. I mean, you can reach to your destination, but you need to wait because of the net. You have some blocking links or routers in your network. We also have this nice trade-off that people have proposed, like rearrangeable non-blocking, that the network is actually can be rearranged in order to make connections. These are also considered as reconfigurable network architecture, that you can reconfigure the design of your network. You can actually reconfigure your topology such that you make some connections that is needed in order to make sure that you don't have blocking in your network. Okay, any question? Now let's see some example topologies. We're gonna discuss some of these topologies. For some of them, I will provide some details. For some of them, I will just skip, but those, hopefully, you will get some insight about why topology is important. We will start with the simplest topology, which is BOS. There are some metrics to evaluate interconnect topology, like the cost of network, like how many routers or how many wires, let's say, we need to spend in order to design our interconnect. What's the latency of interconnect, like the hops in nanoseconds, for example, and how your interconnect works at contention, essentially. And of course, there are many other metrics exist that we should think about, like what's the energy consumption of the network, bandwidth of the network, and overall system performance. And I would like actually emphasize this overall system performance, because the research in interconnection network and network on chip, people have worked a lot to only improve the network performance. But after, which is good, actually. I think that that kind of research is actually needed. But at the same time, we should also think of, okay, what's the effect of that network performance in total system performance? Sometimes when you use this network, like for example, in GPU. So GPUs are designed to tolerate latencies, essentially, because by making it possible that you switch across threads, like context switching quite fast. So essentially, they can tolerate latencies. So if your average, the network latency that you have on average is around, let's say, 200 cycles, and you make some, performance improvement, and you make that 200 cycles to, I don't know, 175 or 150 cycles, which is actually a good improvement. If you only report the performance of the network, you can see that average latency I reduced from 200 to 150. But the moment that you want to see the performance of the system, so you run your GPU application and your network is beautiful because now the latency is 150, but then the overall performance in your GPU application would be something around 1% or maybe less than 1%. Because essentially that 50 cycle is possible to tolerate between using your basically latency tolerability that you have inside your GPU. But if your network latency is around, let's say, 1,000 cycles, and then you make it to 300 or 400, then you can observe some performance improvement. So it's always important that you should see also the effect, or at least analyze the effect on overall system performance. This part, I would say that in early researches in this area, people actually have forgotten, or they didn't simply focus on. But later on, actually, people start to report system performance metrics as well in interconnection works. This is BOS, which you can imagine. Like here, we are connecting 8 nodes to the BOS, all nodes connected to a single link. And this can be actually simply processors and memories. Like we have 4 memory banks and then processor and cache, and these are all connected. So of course, it's simple and cost effective for a small number of nodes. So it's actually cost effective for a small number of nodes. If you have many nodes, then you cannot really make your BOS cost effective. Because as you lengths your as you lengthen your bus, your capacitors and also resistance of that bus is getting larger and larger. And in order to sustain the good performance of that bus or good frequency, you need to add a lot of repeaters and a lot of stuff, such that this bus can sustain good signal integrity. But yeah, and that make this not really cost effective, essentially. And it's easy to implement, and it's also very good for coherence, as you know, for snooping cache, for example, and because it's just a single point of serialization. So everyone can observe what's happening on the bus. But as you can imagine, it's not scalable to a large number of nodes because of limited bandwidth and electrical loading, which in the end, they reduce frequency. And also, it's not very good at contention. So it gets saturated very soon. So when you have only a few nodes, so your bus needs to arbitrate across only few nodes, like 4 nodes. But once you have 64 nodes, let's say, now your bus needs to service 64 nodes. And at each time, assuming that your bus is not hierarchical, so you have only one single bus. So at each time, there should be only one driver to the bus. So not 2 nodes or not more than 1 node should access the bus to write or drive it. There can be many other nodes that they read it. That's why actually bus is very good for broadcasting and multicasting, but you cannot, only 1 node can drive the bus. So essentially, when you want to write to bus or drive the bus, you need to consult the arbitration unit, essentially. And you can see that when you have many nodes, your chance to get the permission to access bus is getting lower and lower. And in the end, your performance is low. So I think a trade-off for bus is actually quite clear, right? Or anyone wants to make another upside or another downside about bus? Which I believe actually we have, but here are just some examples. Okay, good. At another extreme, we have point-to-point network, which every node is connected to every other with direct and isolated links, essentially. So here, for example, node 0 is connected to all other nodes with an isolated link, meaning that node 0 can reach to every other node with only 1 hop and without any contention. So that's the point-to-point connection, essentially. And that's also the same for node 1, node 2, and you can see other nodes. So of course, this has lowest contention, and it has potentially lowest latency. Why is it potentially? Any thoughts? Sorry? There's only one link. Yeah, but that link is not contented, right? Yeah, but you can consider that you have isolated link from 4 to 0. So there can be 2 unidirectional channel or links, essentially. But there is a more important reason. Any other thoughts? Yes? Yes, exactly. That's actually one of the very good reasons. So once that's actually bring me to that part that I said easy to implement or easy to build. So once you want to make this point-to-point connection on your chip, essentially, it's not possible, right? I mean, it's possible, but you need to, some of these wires, they cannot really easily connect to the destination because of the contention of the wire routing, essentially. So then it will make some wires longer and longer, and that long wire would have higher latency. And in the end, you might not have actually the best latency. So I would say that if can provide the best latency, if your network is highly contented. So because then your link latency is not really a bottleneck. We're gonna actually learn about performance metric of interconnect. But interconnect, there are many actually different parameters that they affect the latency of or performance of the interconnect. But essentially, when your network is not loaded, is not contented very much, your latency is bounded by your links latency and those stuff. But when your network is highly contented, like there are a lot of requests going on, then your actual latency is bounded by the queuing latency, right? How much you are queued. I would say that since this network can work the same for zero load and also highly load, At some point, this would outperform many others. But in low loads, we don't know, right? Yeah. In bus, right? So there is a module somewhere that does arbitration. So every node should send a request to that arbitration. And then we have these arbitration cycles that arbitration arbitrates across the active request. It can be, and there can be a lot of different policies. It can be round robin or any other stuff. Yeah. Okay. So, but you can see that it has the highest cost because you have order n connection on ports per node, and overall we have order n square links essentially. So it's very high cost, and it's not scalable, of course. Another nice trade-off is actually crossbar, which actually crossbar tries to make a same performance as point-to-point connection, but provides less, I mean, much less overhead essentially. And that's why actually crossbar has been used in many real processors actually. So every node connected to every other with a shared link for each destination. So that's the main difference here. Here, if you want to connect to node 0, so every node can connect to node 0 with a different or separated link, essentially, right? But in crossbar, if you want to connect only one node, or can connect to node 0 at a given time, because there is a shared bus here. So essentially, you have multiple buses, right, in crossbar, and that makes the difference here. So this enables concurrent transfer from non-conflicting destinations. So as long as your accesses are going to different destinations, you don't have conflict. But if your accesses are going to the same destination, yes, you have conflict. But in reality, that case, you would also have some conflicts because your network might not cause the conflict, but once you get send all this data to that destination needs to process those, right? And then that destination might not have enough bandwidth also to process all these outstanding requests at the same time. So in the end, sometimes we don't really need also, basically, we don't need to provide concurrent transfers for conflicting destinations, essentially. Because that destination node also is not sometimes capable of processing all these requests at the same time. Make sense? So this is it could be cost effective for a small number of nodes again, but this actually has been used in some of the real chips as well. So it's low latency and high throughput. Of course, it's expensive, but it's not as expensive as the point-to-point connection. It's not scalable because it's order n square cost again. So you can see that when n increases, then the cost is actually increases by the power of 2. And we have difficulty to arbitrate as n increases because now you have a shared bus and you need to arbitrate. Okay, so that involves some difficulties. But actually, this use in core to cache bank networks in IBM Power 5 and Sun processors, it's in GPUs also. I'm not completely sure the exact network, but many research papers, they have considered that we have kind of crossbar to connect the GPU cores to the last L2 cache banks, essentially. So as long as the number of cores are not that many, and as well as also number of cache banks, crossbar can be actually implemented in real chips. And this is another view of crossbar design, that you have a kind of these tri-state buffer that you can control which of these tri-state buffer can basically drive the bus, and other would just float the bus, essentially. This is the this network structure in Sun processor that you can check if you are interested. But essentially, they use this kind of crossbar to connect cores to caches. There is also another trade-off in order for designing crossbars. You can, instead of having this design is actually bufferless, right? That you have there is no buffers, and you need to arbitrate. And at each given time, one of these source can access or can drive the bus. But you can also imagine that you have some flow control and then you have some buffers. And essentially these sources can send message to that buffer, and that buffer will put data on the bus. This can potentially basically make sure that you do this arbitration, the arbitration latency can be overlapped by your sending your request, essentially. Because while you are sending your request, arbitration can be also happen in parallel, and at some point your this queue is also getting dequeued, basically, and you put data on the bus. So this, of course, simpler and for arbitration scheduling and efficient support for variable size packets. However, now it comes at the price of buffers. So you need n square buffers, essentially. Make sense? Okay, now the question is that we know that crossbar is good, but can we get lower cost than a crossbar, but with a similar performance, but yet still have low contention compared to bus? And the answer is yes, and people have proposed multi-stage networks that they are very similar to, multi-stage networks are considered in the category of indirect network, as we discussed. This is, for example, an example of one multi-stage network, Omega network. That essentially the idea is that indirect networks with multiple layers of switches between terminals and nodes. So we have some switches here, and each switch can be here, for example, is 2-array, like 2 inputs and 2 outputs. But it can be also 4-array, for example, or 4 inputs to 2 outputs. So there can be many variants of that. And so the cost of this network is actually order n. N is the number of processors, and log n, which actually is here is actually log 2n here, because your routers are 2, like 2-array. If routers are 4-array, for example, it's going to be log 4n, essentially. So that's the cost. And latency is also order log n again here, which makes sense. There are many variations of this multi-stage network, Omega, Butterfly, and so on and so forth. You don't really need to know the exact basic structure of them, but here are just some examples. Interesting thing about this network, for example, Omega network, is a blocking network. So here you can actually see the the definition of conflicting network with this example. So assume that there is a packet sending from this node to this node, and you can see that there is only one path, and that's actually part of this issue. So there is only one path, you don't have path diversity. Now this node 001 wants also to send a node to completely different node, so you don't have conflicting destination, right? But unfortunately, because of your shared path, which you need to get also access this node from this shared channel, this basically green flow needs to wait, essentially. And that's caused these conflicts, which is not good. And people actually have tried a lot to propose a multi-stage network that does not provide, that can mitigate conflicts as much as possible, or make it almost zero, the likelihood. Of course, maybe there might be some cases that you can still, but hopefully those cases is not that probable in normal usages. Yeah, so we already discussed this, that a multi-stage network, basically now, if you think about it, actually in a crossbar, each of these routers, so here there should be a router that, if you think about it, that is n input and 1 output. It's like n-array router, but the output is 1. In point-to-point, you have n-array n input and n output, but here you have n input and 1 output. So that's the difference here in crossbar. But what makes this multi-stage network simpler is that your routers are now, for example, here is 2 input, 2 output. And that's essentially what we have here. Any question? So the way that you implement multi-stage networks, there can be different ways, essentially. So one way you can send your packet, and they traverse through the network hop by hop, and you somehow need to basically route them, buffer them until they get to the destination. But you can also think of circuit switch, which we're going to learn about circuit switching at the end of this lecture, almost end of this lecture, in flow control, that you can essentially, you create a switch, you create a circuit from source to the destination. So you reserve paths and you create a switch, create a circuit from source to the destination. And once your circuit is established, you use that circuit in order to send your messages. We're going to learn about circuit switching very soon, actually. I mean, end of this lecture. And this is packet switch that I already mentioned. Okay, so yeah, I don't want to go into detail of circuits and packet switching here because we're gonna learn about it today in flow control. But essentially, circuit switching sets up full paths before transmission. So establish route, then send data. It's actually exactly the way that we also use in our Venice fork for SSD. We reserve a path and we establish basically transfer from flash controller to the flash chip, and then we send the data. So the problem is that none else can use those links while circuit is set. But in packet switching, it performs routing per packet in each router and routes each packet individually and possibly by different passes. And if link is free, any packet can use it. So you don't reserve a link for packet switching. So of course, circuit switching is faster arbitration. You don't necessarily need buffering, although you might need buffering when you want to create a path, like when you want to establish the path, you might need some buffering for that. But after that, you don't need buffer. And however, setting up and bringing down paths takes time. That's why actually circuit switching is very good when you want to transfer a lot of data from a source to the destination. Many actually prior work, they use circuit switching for streaming accesses, for example. You know, for the streaming access, you know that once you make this circuit, then for a while, this source will gonna send data to that destination. So it makes sense to you establish the circuit, and the overhead of that can be amortized easily. But when you're basically when your communication is not that frequent or that big, it's better to use packet switching, for example. So in packet switching, it's potentially slower. Again, potentially, it depends on the cases. And now you need to handle contention via buffering or many also other techniques that you're going to learn about later. However, you don't have setup and bring down time. So when you want to send your packet, you don't wait. You just if your source router is free, you just send your packet to source router and say that okay, handle this packet for me until you get to the destination. But for circuit switching, you need to wait to set up the path essentially. So let me also quickly discuss the switching versus topology. This circuit and packet switching choice is independent of topology, and it is a higher level protocol on how a message gets sent to a destination. So basically, depending for any topology, like in mesh, you can have switching, both packet switching and circuit switching. And but there are also some topologies that are more amenable to circuit versus packet switching. So that's why actually people design different networks for that. This is an example that you have seen in, I guess, in asymmetric heterogeneous lecture as a Tyler processor. That topology is 2D mesh, but actually we have 5 different networks. And 4 of these networks are packet switch, that they are used for different use cases. These are actually also related to coherence protocol as well. We didn't discuss it actually much, and we are not also going to discuss it today. But essentially, in order to make your coherence protocol work in the network, you need to sometimes you need to design a separate network for response, for acknowledgement, and also a separate network for basically for data. So people now try to make virtual channels in order to give that illusion of different network, but essentially in some design also they design completely different networks. And they also have one circuit switch, which is used for streaming data, essentially. This is also another example of a multi-stage. I'm going to just show some example, and then we can maybe take some break. So this is a delta network, single path from source to destination, and each stage has different routers. And this is proposed to replace costly crosswires as processor memory interconnect, as you know. And you can see the description of delta network in this basically paper. This is also another one, Omega, that we already seen, which is actually used in NYU ultra computers. Very interesting thing about this network is that they actually use this idea of doing computation in the network, which is a very interesting thing. Once you access memory and you are reading your data, you can actually, once you're sending your data is getting transferred through routers or switches, you can actually do also computation on that data. So they actually implement this fetch and add MI, which return M and replace M with M plus I. So as your data is actually traversed through the network, you're also doing some computation. It's really also similar to near data processing, essentially. Butterfly is another famous example of a multi-stage network. It's equivalent to Omega network and indirect. And so conflicts can cause this saturation. So these networks still can cause conflicts. But of course, randomization of route selection can help. So you can try to randomize the routes that you take from source to destination in order to reduce conflicts, essentially. But let's quickly review these topologies. So crossbar that we have seen, multi-stage logarithmic, and mesh. So we haven't seen mesh much. We're going to see more, but you have some idea about it. So these two are indirect. Mesh is direct. Crossbar is non-blocking. This network is actually multi-stage logarithm is actually blocking, and mesh is also blocking. The cost is order n square. This one is order n log n, and this one cost is actually much less, or order n. Latency for this one is O1. This one is O log n, because you need to take log n steps. But this one is order square T of n, essentially. Any question? Yes.
Why is the crossbar? Why is that not?
So crossbar is non-blocking because as long as you don't have yeah, so as long as you don't have blocking destination, so that's the difference. Sometimes your network is blocking, meaning that once you make it pass from one source to the destination, there can be other paths that they cannot use that destination, that path. So as long as you consider that you don't have blocking destination, like not, if you have blocking destination, probably you need to wait. Because your destination, like in the example of flash chip, for example, you want to send a read request to flash chip, so flash chip can service only one read request at the time, right? So anyway, you need to wait. So that's, even though that's also people try to think about it and think about providing non-blocking network in that sense as well. Like, as I said, like point-to-point connection is completely non-blocking, right? But usually people consider a network non-blocking if it can actually provide all possible communication, as long as you don't have conflicting destination. So crossbar is considered as non-blocking because, yeah, as long as you don't have conflicting destination, you can establish any pairs of source and destination. But that's a very good question. Okay, so now we're gonna see some of these direct topologies. But before that, I think it's good to take some break. Let's take 11 minutes break, and we can continue at 2:35.
Our voice is recording.
Okay, let's get it started. So now let's take a look at some topologies that they are considered as direct topologies. So we already seen bus, right? But this is another topology which actually quite useful, and this is ring. So yeah, so with ring topology, you can actually have this wraparound, and that actually provides some path diversity. So assuming your ring is actually bidirectional, because your ring can be also unidirectional, such that you cannot go two ways. But as long as your ring is bidirectional, from this source, essentially between every pair of source and destination, there should be two passes, right? So you have some path diversity, which is good for performance and also for reliability, because if one of these paths basically is faulty, then your ring will be an array essentially, right? But still your network is connected. But of course, it cannot tolerate more than two faulty nodes. So it's still cheap because the order of n, but latency is still high because it's ON, even though latency is lower than array. But when you think of order, it still is order n. And it's also not easy to scale. And bisection bandwidth also remains constant. It's just one, right? There is only one connection, or no, two connections actually. There are two connections. So bisection bandwidth for array is one, bisection bandwidth for ring is two. And that actually remains constant for array and ring as you increase the number of nodes, which is bad. You know, as you make your network larger and larger, at least you think that, okay, bisection bandwidth also should be scaled somehow, right? But if that remains constant, that at some point that becomes your model. But this actually has been used in some processors and many other commercial systems today. This is a unidirectional ring that you can only send packet in one direction. Here is counterclockwise. So again, simple topology and implementation, reasonable performance if n and performance cannot read this. Yeah, essentially, if n and the need for performance is still moderately low, and order is ON as we discussed, and the average hop is n over 2. But of course, you can also have bidirectional rings, and with that, you can reduce latency even more and improve scalability. But it's slightly more complex injection policy. You need to select which ring to inject a packet. So you can have actually two different rings. You can have two different unidirectional rings that they are connected, and then you can decide in which ring you can put your packet essentially. So, and you can think of more rings as well in your system. And that's the topic actually that people have proposed, using bidirectional rings, hierarchical rings, that they can be really useful. The example of one of the Intel's processor, and hierarchical rings that essentially you have different rings, and then you can connect these rings by a ring again, right? So you can think of such topologies, but these are actually very useful topologies, and they have been used. If you want to learn more about hierarchical rings, you can actually check this paper. It's a beautiful paper that you can learn a lot about trade-offs here. And as I said, hierarchical rings has been used in real systems. This is a work from Huawei that they basically essentially use hierarchical rings. Okay, but now let's take a look at mesh. That we always talk about mesh, but we never actually show mesh in a formal way. So this is mesh. Each node connected to 4 neighbors, and most of the nodes. There are some nodes that they don't have 4 neighbors, as you can see. And when you talk about mesh, you always use this north, east, south, and west direction. So up is considered as north, as you can imagine, and then west, east, and south. Cost is ON, and average latency is O squared TN, essentially, as we discussed also in the past. So easy to lay out on chip, which is because it's regular and equal length links. So this is very good for mesh. So as long as you increase your size of your network, and as you increase nodes to your network, you don't need to increase the lengths of wires. That's very good. That's really important. That makes mesh a very suitable candidate for many of these interconnection networks. And path diversity is actually, we have a lot of good path diversity. So many ways to get from one node to another. So for example, if you want to send packet from this node, can you see my, yes. From this node to this node, you have two passes, right? You can go this way or you can go this way. Or for example, if you want to send this packet to this node, then you have more passes. You have this, you have this, you can go X, Y, X, Y. You can go Y, X, Y, X, or many other also permutation. Yes. But all of these are shortest paths, right? You can also do, exactly. You can also go for non-minimal paths. The terminology is non-minimal paths here. And that's actually useful. And we're gonna also see that. Yeah, sometimes I will actually explain that non-minimal paths when I want to talk about trade-off between lengths of paths and also blocking. Because non-minimal paths increases the lengths of these passes, but at the same time, it can be used to avoid conflicts. And with that, you can reduce queuing time. And once your queuing is actually the major bottleneck, you can avoid that, you can mitigate that bottleneck with non-minimal paths. And we have used also non-minimal paths in our Venice work, as you remember, probably. So mesh has been used in some processor like the Intel Tylera and many on-chip network prototypes, actually. So this is Toros. I should also say that in mathematics, we have a basically formula to basically to multiply two graphs. I think it's called Cartesian graph multiplication, if I'm not mistaken. So when you multiply two arrays, you get two mesh network. If you multiply two rings, you get two Toros, essentially. That's also very interesting things about how this field is supported by graph theory and mathematics. So Toros is kind of mesh, but you know that mesh is not, actually, when I said that mesh is not regular, I was confused with this terminology. So mesh is considered as regular network, but it's not symmetric. So there is also another terminology. So mesh is not symmetric on edges, as you know, and performance is very sensitive to placement of tasks on edge versus middle. So Toros avoids this problem, as you can see. So we have also higher path diversity and bisection bandwidth than mesh, but of course it comes at higher cost and harder to lay out on chip. And then you have unequal link lengths as well. Because of these wraparound, these links can be longer. People try to avoid that by wave nodes to make internode latencies constant. So they made a lot of, kind of placements such that this is actually, I guess, for ring. That basically all links now are constant, but at the price of now your latency for every link is actually higher compared to this design, right? So this design, all links are the same. I mean, most of them, like those links that they are in the mesh network, they are the same, but those wraparound, they have longer latencies. But people also made such optimizations that now all links are balanced, but now they are also longer. Another topology is trees. This actually can be considered as the indirect topology, because usually processors and caches are connected to the leaves of this tree. So this is a hierarchical topology, and latency is on order log n, and this is good for local traffic, of course. But if you need to go for longer traffic, you need to basically go to routes, and then that can cause a lot of latency for you. And you know that, for example, for distributing clock network, we are using H3. This is also cheap and easy to lay out, and many works actually has used that. But you know that root can become a bottleneck. So that's why people propose fat tree. As you go to upper levels, basically the bandwidth of the links becomes higher, and links are getting basically fatter and more basically powerful, such that because you have more loads essentially when you go to the root. Right? This is an example of CM5 fat tree, which is a proposal that I can show here actually. Like the data network uses a fat tree topology. Each interior node connects 4 children to 2 or more parents. But here in this example, they consider only 2 parents. And the processing nodes form the leaf nodes essentially of the tree. As more processing nodes are added, the number of levels of the tree increases, allowing the total bandwidth across the network to increase proportionally to the number of processors. So that shows how your network is getting scaled when you add more processors. So when you want to add more processor, you need to increase the number of layers of that tree, and that make your network bigger, meaning that your network has also higher bandwidth. Hopefully, your network also getting more powerful when you add more resources, when you add more processors, that your network can handle the congestion. Question? Okay, now we can get to one of the fanciest topology, hypercube. This hypercube actually is used for supercomputers a lot. I don't know if it's actually used for on-chip networks. I don't think so, because it's not very easy when you want to basically fabricate hypercube on a 2D on a chip. But in a supercomputer, you can actually do that. So hypercube is a n-dimensional cube or n cube, and you can actually use this terminology. Like 0D is a hypercube with a degree of dimension of 0, and it's only 1 node. Then you have 1D hypercube, which essentially you have an array here, but this array has only 2 nodes. Once you have 4 nodes, you can actually make a 2D hypercube, and this is 3D hypercube, this is 4D, and you can imagine how you can go to 5D essentially. But the good thing about hypercube is that latency is actually quite low, is order log n. Like, why is that? It's order log n. Yeah. 3 hops in 3D, right? Exactly. But how you can imagine in n dimension? Why is it n? So the number of nodes is always 2 to the power n. You know, so when you have when you talk about your hypercube as n cube, it means that it's connected n nodes. So then basically your the number of bits, if you want to represent your nodes, like to address your nodes, how many bits you need, or how many attributes, or exactly attributes you need. You need log n essentially. So talking about 2 to the power n nodes, you need n bits to represent every node. And essentially, the longest path is from the node old 0 to old 1, right? And in every hop, you are fixing one of these ones, 0 to 1. And then you need to take n, which is log 2 to the power n. But here, because we are talking about n cube, we are saying that latency is O order log n, essentially. And radix is number of links connected to each router. Radix is O order log n here again, and the number of links is order n log n, essentially. And this is how hypercube is connected. This is actually for 4D. I think actually we use this kind of question for one of the exam. Yeah, but we explain the So you didn't need the explanation here to understand. So we provided enough explanation in the exam draft. So yes. No, they are the same. Oh yeah, that's true. Exactly. Yeah, you're right actually. When we say ND hypercube, it means that it has 2 to the power n nodes. And then yes, exactly. And then we have exactly. This n here is number of processor, which in reality is actually 2 to the power n. Yeah, that's actually a good point. Okay. So it has low latency, but hard to lay out in 2D. This is a cosmic cube, which has been used in one of the supercomputer back then. And you can see how they connect 64 nodes. So essentially, they need to use a 6-dimension hypercube. Okay. Question. Okay, let's now also learn more about routing. So again, we're going to start with some terminology. So routing mechanism can basically it involves arithmetic, which is a simple arithmetic to determine routes in regular topologies. Like what's the arithmetic such that can tell you how to reach to the destination. So somehow you need to address your source and nodes and destination. And there should be arithmetic say that, okay, how you can reach to the destination. Like in a mesh network is easy, right? You just need to, in mesh network, you can actually address each node with a pair of x, y. And then you know that arithmetic is easy. So you just calculate the difference between x and y. And then you know that how many hops you need to take for the x dimension and how many hops to the y. For hypercube is also easy because the address is number of bits. And then the difference between the source and destination is the number of essentially differences in all corresponding bits. And then you need to make sure you need to take hops in order to fix all these differences. But that's actually can be very hard for some topologies. And people propose some topologies, and then they spend a lot of time to design some routing algorithm for those topologies. So it's not that easy sometimes. As I said, for XY routing, for this dimension order routing is easy for mesh and torus, for example. Source-based is another terminology here, which source specifies output port for each switch in route. So you do the routing once at the source router. So you want from this source, you want to send packet to the destination. You don't do this routing algorithm distributed, like at every hop. You just make the path, like calculate the path and put all the routes that this packet needs to take. Maybe you can actually add it to the header of that packet, for example. So that packet knows that, okay, I need to go to the node 2. At the second hop, I need to go to node 3, and then 4, and then I don't know, whatever, 8, and so. So basically, you put all these routers, or let's say, or ports that this should take at the source. Another way is, so this is actually simple and makes your router or switches quite simple because you don't need to do this arithmetic at every hop. You only do it at the source. But at the same time, it makes your header large. Another way is to do table lookup based. So essentially, these are all different ways that we can calculate the routing. As I said, you can come up with some arithmetic, or you can do this routing, you can calculate the source, or you can have this table lookup base. So at every node, you can have a lookup table that just access that table and tell you that which output should you go. So this makes your header smaller, but it can make your switches more complex. But in general, you can also categorize routing algorithm in 3 types. Deterministic, which always chooses the same path for a communicating source and destination pair. So there is no, let's say, adaptivity. So there is always one path from one source to the destination. Another way, your routing can be oblivious. So it chooses different paths without considering network state. Like it's actually quite oblivious. So it's not intelligent, meaning that it doesn't really benefit from, it doesn't handle your path diversity nicely. So just, okay, I have path diversity and I'm just randomly decide based on it. But then you can actually also have adaptive routing. Then you can choose different paths, but this can be adapting to the state of the network, which is, you can see that as we go from deterministic to adaptive, the intelligence in your routing decision is getting better. So how to adapt? You need to know some notion of congestion. So essentially in adaptive routing, you always need a network or a way to learn about congestion in the network. People have designed a lot of way. Sometimes you only care about your your neighbor congestion. You only check the next router, which is downstream router, and say that, okay, how many buffers you have? Oh, you have enough number of free buffers. So I think this path is free, or this path is less congested. But that might be not the best way, right? Sometimes your next hop is actually quite free, but then you get to another hop, which is now, okay, you get to congested roads. So that's why people try to combine kind of local congestion and global congestion. And they actually sometimes design a separate network in order to communicate congestion information in the network. Yeah, and that's why actually interconnection network is not really easy to implement. Also, are you taking minimal passes or non-minimal passes, as one of your colleagues also mentioned? So your adaptive routing can also benefit from non-minimal passes, as we discussed. Okay, now let's take a look at deterministic routing in more detail. So all packets between the same source and destination pair take the same path. Example can be dimension order routing in a mesh network, for example. You first traverse dimension X and then traverse dimension Y. That's XY routing. But in general, for mesh, so that mesh that we showed is actually considered as two-dimensional mesh. So mesh also can be implemented as 3D mesh or 4D mesh, right? So in general, we call it dimension order routing. And when you have 3-dimensional mesh or 4-dimensional mesh, you don't talk about X and Y, but basically you basically resolve the differences in dimensions one by one with the order. So you first fix the difference in dimension 1 and then dimension 2 and then 3 and 4. Of course, you can also have the other way around. For example, here we can have a routing YX. YX is also dimension order routing. But the important thing is that your routing does not make XY and YX at the same time. So it should decide either XY or YX. Is that clear? So this is, of course, simple. And this actually deadlock freedom. Not sure. Yeah, we have a slide for deadlock. Okay, I'm going to discuss deadlock soon. So your routing algorithm should avoid deadlock. We're going to see. However, it could lead to high contention because essentially you only use one path. And also, and it does not exploit path diversity. Even though mesh network, for example, or trust network provides very good diversity, path diversity, but then your routing algorithm does not benefit from that. So deadlock, I think you know the concept of the deadlock in general. So deadlock can happen when there are some resources and there are some requests there. So you need to make sure that deadlock is not happening. But deadlock in interconnection network also can happen, which there is no forward progress. And it can cause by circular dependencies on resources. Each packet waits for a buffer occupied by another packet downstream. So you can actually see from this example. Packet 1 wants to take this path. However, this buffer is not free because there is a packet here that wants also to take this path. This packet cannot forward because there is also another packet that wants to take this path. This buffer is also not free because there is a packet that wants to take this path. And then now you have packet 4 that wants to take this path. So essentially, you have these circular dependencies. that can cause deadlock, right? Sometimes some of these topologies are more, let's say, susceptible to deadlock. Like mesh is not that susceptible. So if, as long as your routing algorithm does not create cycles, you can actually make sure that you don't have deadlock. We're gonna see. But like XY, for example, is a deadlock-free routing algorithm. But topologies like TROS, since you have circle in your topology, so your topology has circles, right? So even using XY routing can cause deadlock for TROS network, and people have working on it, to avoid deadlocks for TROS network. So in order to handle deadlock, you essentially need to you can have different approaches. One is that you want to have deadlock avoidance technique. Essentially, you don't allow deadlock to begin with, so you should avoid cycles in routing. So meaning that you need to use some routing algorithm such that you don't get to deadlock situation. Like dimension order routing cannot build a circular dependency in 2D mesh, for example. But as I said, it can make a circular dependency in torus network. You can think about it as a homework option. Or for example, so that's because actually XY restricts the terms in each packet can take. Maybe I'm gonna use actually Blackboard here, because then we also have this term model, which is actually quite interesting. But another approach is that you can avoid deadlock by adding more buffering that create escape passes. So, for example, as I said, in a TROS network or ring, you have this wraparound, and that makes a circle, right? So if you consider that this wraparound always takes different buffers, so you add some buffers, and whenever you want to take a wraparound, you go to another buffer, right? So that means that this buffer does not go to the same channel. Essentially, you have two networks. These virtual buffers or virtual channels, you can consider not virtual buffer, they are virtual channels, because you are adding channels, but they are not physical, they are virtual. And those can actually avoid deadlocks as much as possible. And another way is actually you let deadlock happen, but then at some point you need to detect it and break it. This is actually good, can be good, because in many cases, deadlock doesn't happen much. So the likelihood of getting to the deadlock situation is not that much. So people say that, okay, I'm not gonna do deadlock avoidance technique. I'm just let packets to be transferred as the way that they can. But then I have a technique to detect that is deadlock happening or not. And if it happens, they need to break it. So Duato algorithm is actually one of them. That I think I have some slides for that. Any question here? Yes. 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 No, actually, deadlock is happening more in packet switch, because you do need the space in the downstream router in order to forward to downstream router. But the resources in downstream router might be busy, because there are some packets that they want to also forward to another router. And if you continue that and make a circular requirements, then at some point no one can basically forward, right? In circuit switching, once you establish a path, then you don't have deadlock. But of course, the way that you establish the path, that can cause deadlock. Because for circuit switching, you need to send a header fleet or things like that, to establish a path. And that can actually cause deadlock. So you should be careful. But overall, people consider that in circuit switching, we don't have deadlock, because, okay, you make the path, and that path can, send your data essentially. But before establishing the path, you might get to deadlock issues. Very good question. Okay, so let's see. Do I have time to use Blackboard? I guess so. What should I do? I think I should stop sharing. I want to basically discuss this term model technique. Okay, and then I mute projection. Okay. Okay. Is it visible when I this way? Is it visible from that side? I hope so. So in a mesh network, so if you consider this is nodes, then essentially for every packet, you can think of, depending on which turn they can take, you can think of clockwise turns and counterclockwise, essentially. So for counterclockwise, you have this north-east turn, east-south, southwest, and west-north terms, right? And for a counterclockwise, you have essentially north-west, west-south, southeast, and east-north, basically terms, right? So now, if you let your routing to take all these terms, you can see that you can get to these circular dependencies, right? So one way to break these circular dependencies is to restrict some of these terms, right? So let's start with XY routing. So with XY routing, we know that XY is deterministic, right? And you always need to take X and then Y. Can you tell me which terms we are omitting in clockwise and which terms we are omitting in counterclockwise with XY routing? Yes. Yes. Exactly. And why? Can you explain? That's true. Is that clear, right? So essentially in XY routing, you only in a clockwise terms, you only have east, south, and west, north. And in counterclockwise, you only have, what are the terms? Yeah, you have west, south, and east, north. Okay. But here we are omitting too many terms. So we only allowed 4 terms out of 8 terms. That's why in XY is actually deterministic. But we can actually make it partially adaptive, like, to use some path diversity, and it still does not allow deadlock. And that's the concept of the term model theory. So for example, you can, yes, you can actually omit 1 term from each of them, but that's not that easy because you need to be careful. I'm going to show a picture when I project again, that the remaining terms, combination of them also can make it circular. So if you allow 3 terms here and 3 terms here, combination of these terms can make a circular dependencies that we're going to see. So you cannot easily randomly remove 1 term from each of them. But for example, one of the famous routing algorithm, which is deadlock free and also considered partially adaptive, is west first. So west first is actually is one of them. And what he says is that if you want to go to the west, you need to first go to west, and then you can go to north and south. Essentially, he says that if you want to go to west, you need to be XY. And if you want to go to east, you can be adaptive. Which means in best first algorithm, we omit terms that we turn to west after that. So essentially, we basically north west is not allowed, and southwest also is not allowed. So northwest is from this circle, and southwest from this. So this is one of them, which is proven to be deadlock free. And actually, the performance of west first is better than XY. But then the issue is that west first is not balanced. So if you go to the west, you are deterministic, and you go to east is not is adaptive. So people also come up with many other variants of that, like odd even. You can search if you're interested. But those are those provide better adaptivity. Any question? Was that interesting? I really like this topic because it was the first research topic that I've done in 2011. It was nice. We work on a extended term model. So we extend this term model theory to bigger stuff, and we used. Okay. Hopefully I'll be able to share. It's all good? Great. Okay, so I already explained this term model algorithm. So the idea is that we analyze directions in which packets can turn in the network and determine the cycles that such terms can form. And then we probe just enough terms to break possible cycles. So this is actually proposed in this ISCA paper. Here are some examples. Like this one is that we basically allow every term. This one is XY routing, which we already discussed. And this is actually an example that says that if you randomly cut terms, this can actually get to deadlock. So here, even though we remove one term from here and one term from here, the remaining of terms, they can actually cause a deadlock. And you can see that. Okay. Yes. It's actually proposed for NRE, for n-dimensional mesh networks and process, but mostly mesh, yes, but not 2D mesh only. It can be proposed for 3D, 4D. Okay, so oblivious routing, and one version of them is variance algorithm. So the goal is to balance the network loads, but at the same time, we don't want to impose a lot of overhead. So the idea is actually quite interesting here. So you randomly choose an intermediate destination. So you have a source and destination. You just randomly select an intermediate node, and then send your packet to that intermediate node. And then that intermediate node should actually probably eject your data or put it on some buffers that they are not in the main network. And then you can, that intermediate node can also send your basically packet to the destination. So with this variance routing, you can actually have deterministic routing, but still you can benefit from some adaptivity. Because you send your packet to the destination, it can be deterministic. Sorry, you send your packet to the to that intermediate node, and that can be deterministic. And then from that intermediate node, then you also use another deterministic routing. So you can overall basically balance the load. So it randomizes and balances network loads. And this is actually non-minimal because depending on which node you select, it can actually cause make your path non-minimal. There are also some optimizations. So we do this only on high load, for example, when basically that conflicts and blockings are the major bottleneck of the latency. And we can also restrict the intermediate node to be close in the same quadrant, for example. These are some papers from Valiance that you can check. So for adaptive routing, as we said, it tries to adapt your routing chooses based on the status of the network. It can be minimal adaptive, that router uses a network state like downstream buffer occupancy to pick which productive output port to send a packet. It can be many other metrics as well, like how busy is your crossbar in the downstream router, or how many buffers you have. But it can be also non-minimal, fully adaptive. Also, people call it fully adaptive and it's non-minimal. Essentially, you also allow misrouting packets to non-productive output ports based on network state. So one of the topics that you're going to actually see next week, when we want to design bufferless NOC. So when your network is bufferless, it means that you cannot wait, right? There is no buffer such that you can wait. So how you handle conflicts? You have this idea of routing, which we call it hot potato. It's very similar to hot potato, right? You get a hot potato and you just pass it to another one. You don't care that who is you are just giving the potato. So Nico has worked on that hot potato thing, right? Bufferless NOC in your master. You've been working on that topic, I guess, at some point. A little bit, yeah. Yeah, we've been discussing, I remember. So yeah, hot potato, essentially that's the routing algorithm. And it's actually used for bufferless NOC because you cannot wait, right? So this packet is a hot potato for you, and you need to just pass it. And hopefully you're pass it to the destination, but you can also misroute it sometimes. Okay, so minimal adaptive should be aware of local congestion and also a global congestion, but minimality restricts achievable link utilization, and as you can imagine. Non-minimal adaptive can achieve better network utilization and load balance, but now you need to guarantee live lock freedom as well. So adaptive routing actually has this problem of deadlock, which we discussed a little bit how we can avoid deadlock, or we just let deadlock happen and then we detect it. Of course, the effectiveness of that also depends on how effectively you can detect deadlock. Sometimes you are conservative, sometimes you are not that conservative. But when you have a non-minimal fully adaptive, in addition to deadlock, you might have live lock freedom, live lock issue as well. Like your packets are just transferring in the network without getting to the destination. It can easily happen with hot potato, right? I mean, hopefully at some point your potato is not that hot and you can, eject it. But I'm not kidding. I'm kidding, but you can see some analogy from this, right? So when your packet arrives to the destination, you can basically eject. Okay. So an adaptive routing is, as I said, is also very good for reliability because you can avoid faulty links and routers. The idea is that we can route around faults. So it might be the case that your network is faulty. Sometimes your router is faulty. Sometimes your links are faulty. So there should be a technique that understand what are the faulty components. And then with adaptive routing algorithm, you have this possibility to bypass and route around the faults essentially, and such that you can get to the destination. With deterministic routing, this cannot really happen because your routing is deterministic. And you need to change the routing table to disable faulty routes, assuming the faulty link router is detected. But yeah, you can check this paper from in NOx 2015 about how we can use adaptive routing algorithm in order to resolve faults, essentially. Okay. Yeah, before starting buffer and flow control, I'd like to give another break. Let's have a 5 minutes break, and then we'll start at 3:25. Okay, so let's also quickly discuss buffering and flow control in network on chip. We already discussed a little bit circuit switching and packet switching, and and these two are actually there are pros and cons, and that's why people have tried to use them. I mean, both at the same time in a heterogeneous design, in order to, because each of them is better for some specific traffic patterns, and this is an example that we discussed. But now let's take a look at packet switch network in more detail. So we have this packet format, and essentially we have header that your routing and control information should be stored in the header of that packet. And then you have a payload which carries data, this non-hardware specific information. For example, for your write request to the cache, right? So your payload can be data of cache block that you want to write to your cache, and can be further divided. Like you can do some framing protocol stacks, like divided to fleets maybe. And also you need to add some error code in order to make sure, check that your data has been arrived to the destination with no error or so. And this error code usually added to the tail of the packet. So this is the packet format. So people usually say header, and this payload is also considered as body. They say header and some bodies, and then tail. And that tail can be also tail and body. So there are many different ways to implement it. So as a related point here, we have this contention. So two packets try to use the same link at the same time. You can see the packet from up wants to go to west, and south wants to go to west. So these two packets are trying to use the same link at the same time. So what do we do essentially? So we can buffer one of them, or we can drop one of them, which is not happening actually usually in network on chip. In network can actually happen. Sometimes our packets are dropped and we need to redo the communication. But normally in network on chip, we don't, or interconnection network, we don't drop packets, we usually buffer. Or we can misroute one using deflection, as we already discussed, these hot potato things. For example, you can misroute. And of course, is there a trade-off between them? And the answer is yes. Of course, there's a trade-off. Like buffer is good, but it's expensive. So if that contention is not happening very frequently, sometimes you prefer to misroute, right? Or drop, or even drop. Of course, when you drop, you need to inform the source such that you drop that packet, and that needs to resend the message. But if your contention is actually quite probable, you might want to have buffers essentially. So there are many different flow control methods: circuit switching, bufferless, packet or fleet-based, which you're going to learn about it a lot next week. Store and forward, which is kind of packet-based switching, and the virtual cut-through, which is also another variant of packet-based switching, and wormhole, which is also another way of packet-based switching, with this difference that you operate on fleet. Basically, your flow control granularity is on fleet, and fleet is part of packet essentially. Like it can be header fleet, body fleet, tail fleet. So let's quickly revisit circuit switching. Resource allocation granularity is large. So the idea is that we pre-allocate resources across multiple switches for a given flow. We need to send a probe, or let's say header or whatever, to set up the path for pre-allocation. So no need for buffering. Once you establish your path, you don't need to buffer. That being said, usually you add buffers in order to, because you don't want to have a long combinational links, right? Combinational circuit to the destination, because combinational circuit is noisy. So you want to, and also your frequency of this circuit might be low. So then people add some buffers in between in order to break that combinational circuit. But then you don't need buffer in the sense of, you need to schedule buffer or arbitrate across buffer access, because that buffer can be actually considered as some registers, essentially, the one that we have in circuit switching. There is no contention when you establish the network, the paths, and it can also handle arbitrary message sizes, which is again very good. So in packet switching, we are actually bottleneck. I mean, we are bound by the packet size, and there is a fixed size. Usually there is a fixed size for packet, or there is a maximum size for packet, because you need to design your resources based on that. If your message is bigger, you need to usually separate it in several packets. But with circuit switching, you don't need to be worried about that. You just establish a path, and then you send your message. It can be 2 megabytes, it can be 1 kilobyte or whatever. So you just send your message from source to the destination. However, it has a potentially lower link utilization. Two flows cannot use the same link. And handshake overhead to set up the circuit, of course. And you can see that this circuit switching is actually coming from analogy that we had in the past with telephone network. Does anyone know how the telephone network has been built in the past? Like there were a lot of switches, and from source, you were controlling all these switches in between, such that you can get a pass from source to the destination. And once you establish a pass, then the destination phone will ring, and then you can talk. And there is actually a pass circuit from source to the destination. I mean, of course, it's not like that nowadays, but in the past was like that. And this circuit switching is very similar to that, essentially. So bufferless deflection routing, I'm gonna provide very basically a brief overview of that here. So the key idea is that packets are never buffered in the network. And when two packets contend for the same link, one is deflected, essentially. So this is destination. These two arrive to this, and then one of them is deflected. So new traffic can be injected whenever there is a free output link. So which is good. So in bufferless deflection routing, input buffers are eliminated, and packets are buffered in pipeline latches and on network links. Yes. Two packets. Okay. Yes. Yeah, you can also deflect it. You can. Yeah. I mean, yeah, that needs some support, but it is possible that you just. Okay, so instead of input a lot of these buffers, you just basically you get rid of all these buffers, and then you need this deflection routing logic such that you can get to the destination or without buffers. So you can see from this paper, but we're gonna also discuss it in more detail next week. So issues in bufferless deflection routing is live-like. Live-like is not only for bufferless, but in any routing algorithm that you have some non-minimal routing, you might get to this live-like issue. And you also have now you have some router complexity because of handling these issues and performance and congestion at high loads, essentially. So once your network is congested, you need to deflect a lot of requests, and that can cause issues. You can check the paper for more detail. We have actually improved this bufferless NOC in many different papers. And at some point, we come up with a hybrid solution such that you have bufferless, but maybe adding a little bit buffer can free a lot of issues, essentially. So you don't need to be extreme, right? One extreme is that add many buffers, another extreme is that no buffers. So sometimes something between, just a little bit buffers can provide a lot of good performance in high loaded things. So of course you can check papers for more information about it. And this paper also discussed bufferless routing in hierarchical rings, essentially. And we also wrote a book chapter on bufferless and minimally buffered deflection routing. And you can check all these summary papers. Okay, so another flow control is the store and forward. Essentially, this is actually part of packet switching. So this is, first of all, is packet-based flow control. And it's store and forward. Essentially, for your packet, you need to send your packet to completely to another node, and that node needs to store your packet completely and then forward it. So you can see it actually from this animation here soon. But essentially, it leads to high per packet latency because you don't pipeline your packet traverse. So your packet needs to be arrive completely to the next node and then send it. So you have per packet latency, and it requires buffering for entire packet in each node, which might be expensive. So if your packets are large, you need to have enough buffers per packet, per node, such that you can store the whole packet completely. So here is this example. So you send the packet completely to this intermediate node, and then you can forward it. Store and then forward. So then the question is, can we do better? And of course, we can do better. We can try to pipeline it. And this is a cut-through flow control, another form of packet-based flow control, but we can start forwarding as soon as header is received and resources like buffer and channels are allocated. So you send the header. So this can pipeline the transmission. So you send the header. Then when header arrives to the intermediate node, you need to calculate routing, and also you need to allocate channels and buffers. But once these things are done, you can actually send the header. And hopefully you can try to have a nice pipeline here, right? So this can heavily reduce the latency. And actually people try to devise a lot of optimization for this cut through with speculatively using all these speculative and look ahead techniques, for example. They try to do the routing look ahead. So once we are in this, when header is sending to this node, we also do the routing for the next hop look ahead, such that we can, we are one step forward. And also, when you want to take the output channel, you can also do it speculatively. So you can speculatively assume that, okay, you're going to get the allocation slot. And then that can provide much better, best latency. But at some point, yes, I mean, your speculation does not work and you need to wait, essentially. Okay, so the issue with cut-through flow control is that when the output port is blocked, we need to wait, and basically the whole tail needs to be buffered. So still, cut-through flow control needs to have buffers, like enough number of buffer slots in order to buffer the whole packet. So this requires a large buffer enough to hold the largest packet. And this might be an issue, specifically in the past, that designing buffers was not that, as easy as today. So people come up with this another flow control, wormhole, which was actually quite important and useful in the past. Now, actually, we are a combination of them. Like if whatever we have, wormhole switching and virtual culture are actually more or less the same now, because we usually have enough number of buffers. Of course, if we want to design bufferless, that's another story. But once you have buffers, people can add enough number of buffers. So in wormhole, the difference is that your flow control is based on fleets. So fleets are sent across the fabric in a wormhole fashion, like the wormhole, and body follows head and tails follows body, and this is in pipeline. And if head blocked, rest of packet stops, and the whole packet is actually stopped in the whole network, essentially. In all these routers that you have in the line. So that's why actually in wormhole switching, once if you have only one buffer, then actually it's not that good, because once you have blocked, basically the whole packet is actually is occupying many routers, and that's not good. So people try to. It's good that with wormhole we can get rid of that criteria that you need buffers that can accommodate the maximum packet size, because sometimes there might be some packets that they are very large. So people say that, okay, we can try to have wormhole switching, but at the same time we can have also a lot of buffers. So our buffers, for example, are good enough or large enough in order to accommodate average size packets. But once we have sometimes quite large packets, then okay, we don't need to have physical buffers for them, and then we can use that. So you can think of, so wormhole is very good that break that restriction essentially. So now the question is that how does body and tail know where to go? So they essentially follow the head. So we need to we need to store this state in the router, and latency almost independent of distance for long messages. Why? Because you make a pipeline, so you need to spend some time for the header fleet to reach to the destination. Basically, header fleet needs to go all these hops one by one to reach to the destination. But once the header arrives, hopefully every cycle you will get another fleet. So then that's why actually, especially for long packets, for large packets, the number of hop is not really an important metric for the latency of that packet, because it's only defines the latency of the header fleet. Other fleets are pipeline and they will arrive to the destination every second. Is that clear? Good. So, of course, the wormhole has advantages over store and forward flow control. So it has lower latency and more efficient buffer utilization, but it has limitation. It suffers from head-of-line blocking. If head fleet cannot move due to the contention, another worm cannot proceed, even though links may be idle. So here is an example. So you have these input queues. Let me remember. Oh yeah. So these ones, they want to go to output 1, and these two wants to go to output 2, I guess, if I'm not mistaken. Exactly, yeah. So basically these ones, they are bottleneck because one of them will get the, okay, let me rephrase it. So you have two input queues. This one in this queue wants to go to output 1. This one also wants to go to output 1, right? So this two needs to be arbitrated, and this one gets the permission. So this can go to the output 1, but this one cannot. So this one here needs to wait, right? So the next fleet that we have here is actually wants to go to output 2, but this cannot proceed because of head-of-line blocking, because we have a queue here. So since 1 is blocked, this 2 is also blocked. So that's actually the issue of head-of-line blocking. And how people handle that, they come up with virtual channels. It's actually also, you can see head-of-line blocking here with this animation. You can check it. But then how people design it is actually using virtual channels. So virtual channel flow control, the idea is that we multiplex multiple channels over one physical channel and divide up the input buffer into multiple buffers sharing a single physical channel. This is virtual channel flow control, or virtual cut through, as people also say. So these are your buffers. So you made each buffer to some parallel buffers. So you call them virtual channels. So previously you have one FIFO buffers for that channel, and then you can actually break that FIFO buffer to many in parallel virtual channels. Of course, now you need to decide between all these virtual channels, and that make your router more complex. But of course, it can eliminate head-of-line blocking to some certain. You agree? Because you can allocate virtual channels to different flows or to different worms, essentially. So here is an example. I don't want to go through all this. Yeah, essentially, okay. So this blue flow wants to go down, but cannot because of this blocking. But now red flow, actually, since we put it on a different channel, different virtual channel, red can actually proceed. So that's the efficiency of this virtual channel. And this is a modern virtual channel-based router that every input channel is demultiplexed across different virtual channels. And then you have a multiplexer that you select one of these virtual channels to go through the crossbar, essentially. It's a virtual channel-based router in 2D mesh, essentially. But virtual channel actually is good for head-of-line blocking, like to avoid head-of-line blocking, but they also have other uses. One of them is deadlock avoidance, which I already kind of actually mentioned. So you can enforce switching to a different set of virtual channel on some terms, can break the cyclic dependency of resources. Like when you want to go to the wraparound in a throws or ring, you can take another virtual channel. Or you can have different sets of virtual channels, saying that, okay, at the next, when I'm taking the first hop, I have all the virtual channels available. When I get the, then after one hop, I have only one virtual channel is not available for me. After second hop, another virtual channel is not available. And then at some point, so you're reducing number of virtual channels as you go to the network. And that actually can remember you something similar to, if you want kind of analogy, you don't make a circle, you make such things, you know? So it's not until you get to the destination. It's very similar to that, actually. Okay. You can also allocate some virtual channel as KBCs, which is actually proposed in Duotto's algorithm, if I'm not mistaken. Like in you let all packets to take every basically passes, like fully adaptive routing. But once you detect a deadlock, you have some escaped virtual channel, and those virtual channels they are using deterministic routing. So you just put your packet to those escape VCs and say that, okay, now this packet needs to go to escape VC and then will be routed to the destination with deterministic routing. So that's actually Duotto's. Duotto is actually one of also the founder of this field, I would say. So yeah, that's actually one of the the algorithm that Duotto's proposed for providing this adaptive routing with not a lot of cost. Another very important topic is protocol level deadlock. So we discussed about cache coherence protocol. So your network might not have a deadlock, but once you implement cache coherence protocol on the network, you might have deadlock at the protocol level. I don't want to go into detail because that needs a lot of time to explain. But people actually come up use different virtual channels, as I said, for these different messages. That's actually why we have different in Tyler. We have different networks for reply and messages. So you can also think of different virtual channels. When you want to send some of these acknowledgement and some of these coherence requests, you can use different virtual channels, different set of virtual channels. People, for example, come up with solutions of using 3 virtual channels in order to make some of these basically a coherence protocol work, essentially. Okay. And also you can make some prioritization of traffic classes. So once you want to prioritize, you can actually have some virtual channels that they have higher priority. And if your flow is more important, you can make sure that that flow only uses those virtual channels. Because those virtual channels are prioritized, meaning that in your arbitration policy, in your allocation policy, for example, you can prioritize those virtual channels, meaning that basically you give them a slot more and more. Okay. So this is a review of flow control, store and forward. And then we go to this cut through and wormhole. And we also discuss about this head of line blocking that we can avoid with virtual channels. Okay, another issue here is that we need to communicate buffer availability. We can have different technique here. One of them is credit-based flow control, that upstream knows how many buffers are downstream, and downstream passes back credits to upstream, essentially. And there should be significant upstream signaling, like special for small fleets, essentially. So you need to communicate between upstream and downstream such that they know how many buffers are available. Another flow control can be on and off. That downstream has on-off signal to upstream. Just say that back off, don't send anymore. And it can be also ACK and acknowledge flow control. So upstream optimistically sends downstream data, and then buffer cannot be deallocated until ACK and NACK received, right? So downstream needs to send acknowledgement or acknowledgement to the upstream router. Okay, so here is an example. But we have 2 nodes here, and this is the timeline. So node 2, there are some fleets in node 2, and these fleets departs from that router, and then node 2 communicate. So now after some time, node 2 realizes, okay, now I have more buffers. Then node 2 will communicate that new credit to node 1. So this will also take some time, which actually called as credit delay. And then node 1 needs to process that credit and said, okay, now I have this node 2 has enough credit, so I can send my fleet to node 2. And after node 1 send this fleet, now node 1 also realized that, okay, now I have more space, so I can send credit to the previous router of node 1. So, and essentially this can happen. And this called as credit round trip delay, essentially. So round trip credit delay is time between when buffer empties and when next fleet can be processed from that buffer entry. Significant throughput degradation if there are few buffers, and important to size buffers to tolerate credit turnaround. That's why I said that even with wormhole switching, people try to have enough number of buffers such that these credit-based flow control, or essentially flow control, can work easily with better performance. Another way could be on and off flow control. So downstream has on-off signal to upstream. So node 1 is sending fleets, and then at some point node reaches to the basically off threshold. So node 2 sends off signal to node 1, and then node 1 stop it. But basically node 2 should send it proactively, because it will take some time, right, to arrive. So node 2 send this off signal, like predicts that soon I shouldn't be able to, or I don't have enough capacity to store fleets. So node 2 proactively sends off signal, but in the meantime, node 1 sends packets. At some point, node 1 observes off and then a stop. And then basically at some point, node 2 also traverses some other fleets. After some time, then we get to another threshold, which is F on, and then send the on signal to node 1. And node 1 start process it and then keep sending fleets, essentially. Is that clear? Okay. Good. I think we have enough time to cover the last part, hopefully, and then we will conclude today. So now let's quickly also discuss interconnection network performance. This is actually a very interesting curve that we have in any latency load system. Essentially, you have in your network, you have an injection rate into the network, or amount of load on the network, like how many packets you are injecting to the network. And that's the latency, which is like the average network latency or average packet latency that we have in the network, right? So the thing is that there are many parameters that define this network. We have minimum latency given by topology. So every topology has a minimum latency, as we discussed, like the diameter, like the average distance or whatever. So all these are dependent on the topology. And then we have a minimum latency given by routing algorithm. So your routing algorithm also can add some inefficiencies on that topology. And then all these topology, routing, and plus flow control, basically all they define a latency, which we call it zero load latency, meaning that if you have no conflicts or no blocking, this is going to be your minimum latency in the network, right? But then at the other side, also you have a throughput, which is given by topology. So each topology has a maximum throughput, can theoretically sustain. But then your routing algorithm might not be that intelligent enough, so it can actually reduce the bandwidth of that, like the throughput of that network. And then essentially, all these flow control also can reduce your throughput. So that's also the maximum throughput that you can get. So we call it saturation throughput, that injection rate at which latency asymptotes, right? And this curve is actually quite exciting, that we always see when we want to analyze the performance of network on chip or interconnection network. So the ideal latency, you can actually check this formula, but it's actually kind of makes sense. So it's solely due to the wire delay between source and destination. That's your ideal latency. That D is your Manhattan distance, which is distance between 2 points measured along axis at right angles. It's actually coming from like the Manhattan map, like the grid that you have. And V is the propagation velocity, like how fast you're sending information. L is your packet size, and B is your channel bandwidth. So this might be, it is going to be your ideal latency. You can check. But then actual latency is dedicated. So because we have wiring, like we have impractical in wiring. So long wires segmented with insertion of routers. So in our router, we have so we need to go through all routers. So then Manhattan, in addition to this ideal latency, you also need to consider the number of hops and the latency of each router, T router, and TC is latency due to contention. So you might also have some contention. But you can see that actually we pay for hops times T router only once, because we are using kind of wormhole or virtual cut through that we pipeline things. This is your actual latency. But things that if you do some experiment, you're going to see that this actual latency is actually this. But, this is your ideal latency, but this is your actual latency because of the routers that you have in zero load. But then as you increase the load, your latency is getting higher and higher. And at some point you get to saturation point. And this x-axis here is injected load. People use different metrics. One of them is like number of packets per node per cycle, like how many packets you're injecting, like to the network. Here also another metric, which is injection load, fraction of capacity. If we know that the capacity of our network is something and we call it 1, this shows that how many basically packets or what fraction of that total capacity are you using. So now you can see that actually like we are saturated around 70% of the capacity, which is actually quite good. Sometimes there are some networks for some specific route traffic patterns that we get saturated very early, like 30% of the capacity or even earlier. So here are some examples of load latency curve with different traffic patterns. These are some synthetic traffic patterns that people come up with, and they use these different synthetic patterns to somehow model the actual traffic patterns that we have in real life. But some of them are also quite theoretical, so they are might not be that meaningful in real examples. And you can see that depending on the traffic pattern, depending on the load and topology, here we consider only, I guess, one topology. No, actually, we consider different topologies, like 256 node mesh, C mesh, which is concentrated mesh, that is the mesh, but like 4 routers 4 nodes are connected to one router, essentially. So 4 processors connected to one router. If C mesh is 4, for example, in this example, and then these concentrated nodes are connected in a mesh network. So we call it C mesh. It's C mesh with C4 here. It can be C8, C16, C2, or whatever. So you can see that with different topologies and different traffic patterns, essentially we have different saturation points. You can check this stuff from this paper. That show a lot of these topology and also these routing algorithms, and showed all these load latency curve from this paper actually. And once you have a new design of network, which is this MEX, which actually quite effective topology, I would say, because it's very similar to C mesh, with this difference that you add some express channel essentially, right? So you have some channels that can reduce the diameter of the network. And the difference here is that these express kind of channels are not that expensive as this flattened butterfly, because they are actual channels, different channels, but here you are reusing these channels essentially. So you can see that these channels is segmented across these lines. You can, of course, check the paper for more detail. But once you have a better design of the network and routing algorithm and also flow control all together, you can hopefully get to design of scalable NOC that can actually handle, basically a system that we have many cores. and that can provide a scalable and scalable solution, and hopefully, and also guarantee services. Okay, so these are some good readings, and these are also some performance metrics for network. Packet latency people usually use, which is you can report average, maximum. Also, you can report tail latency for packet. You also have round trip latency, which is how long does it take for the whole message to receive. Like sometimes you have this request and reply, like this is round trip latency. And then you can also report saturation throughput, which of course is also important, especially when you want to see how your network behaves in high contention loads. But at the same time, there are also some performance metrics that they are at the application level, like execution time. That I already said that why it's important to report execution time, or for example, IPC, system performance, sometimes also job throughput in the end, which are affected by interference among threads and application. Any question? Okay, so I think that includes today's lecture. We are exactly at 4. So if there is no burning question, I think have a nice weekend and see you all next week.